Right. Hi, everyone. Good morning, afternoon, or evening, wherever you are, and thanks for joining me. My name is Catriel. I'm a software engineer on Facebook's privacy team, and today I'm going to be talking about DELF, which is our system to help ensure that we implement deletion correctly across all of our products. As always, this is joint work with colleagues at Facebook and elsewhere, so thank you to everyone. The ability to delete data from online services is a core user privacy expectation. Deletion is simple to understand and straightforward to invoke. And past research has demonstrated that deletion is widely used across online services. People trust these services with their data, and when they're no longer confident they want their data to be online, they delete it and expect deletion to work. And yet, mistakes when implementing deletion are common. These mistakes affect many kinds of services, and we show here some recent examples of news coverage when things go wrong. Each of these mistakes can undermine user trust. So why is it so hard to get right? Let's look at a relatively simple social interaction. On the left, a Facebook post, and on the right, how the data are represented in the back end. So the circles represent objects in Facebook's graph database, Tau, and the lines represent edges or associations between those objects. And let's say now that the post creator decides to delete her post. If you were the developer in charge of implementing deletion, what would you do? So one option is to leave the rest of the graph intact. And indeed, this is intuitively sensible. Why should deleting Alice's post also delete Bob's comments, or Kathy's comments, or Bob's like? What if Bob logs in the next day and wants to see his old post comments? But in fact, this is not the right answer. The right answer is to delete all of the blue circles on the right. And the reason for this is that otherwise the comments would no longer be visible, because the post that they were made on is gone. And if the comments are no longer visible, there's no need to hang on to them any longer. But even if a developer gets that right, they need to correctly implement a cascaded deletion across all of these edges. And you can imagine a viral post might have millions of comments, shares, likes, and so on. Well-meaning developers will get this wrong. And what happens if, years later, another developer comes along and wants to add photo comments, or reactions, or polls? So that's one reason why it's so hard to get right, because even figuring out what you should delete is complicated. But there are many other reasons as well. The impact of getting deletion wrong is high, changes are frequent, data can be stored in many distributed data stores, and so on. Developers need to overcome all of these challenges. To the best of our knowledge, there's no widely known approach to help them. Modern distributed data stores offload the deletion implementation to the application developer. So the data store says, we will implement a point delete API, but you, the application developer, must figure out when to invoke that API and with which arguments. So this leads to 4 common types of mistake that we want to prevent or mitigate with DELF. The first is an outright omission, that is data being left behind upon deletion. Maybe you build a delete button for a post like before, but you just forget to make that delete button also delete the comments on the post. This might sound silly, but that's the default behavior when you're working with any modern data store. Think MySQL or RocksDB, Cassandra. Developers need to take an action to implement deletion when they're storing user data. And the underlying database, Cassandra, doesn't guarantee that developers take this action. The second type of mistake is accidentally retaining data that should be deleted. That's the example we talked about on the last slide. The third type of mistake is accidentally deleting something. The result of this can be catastrophic. This can lead to data loss, and a restoration from a data store backup can be operationally demanding or even outright infeasible. Unless you can mitigate these mistakes easily, implementing deletion actually introduces substantial risk of deleting the wrong data. And the fourth type of mistake is configuring a data store correctly, but not actually executing that configuration. So we talk a bunch more about this in the paper. There's some really interesting engineering here. But for this talk, I mostly want to stick to the other 3 kinds of mistakes, the semantic mistakes, if you like. All right, so that's the problem space. Let me tell you about how we solve it. So how do we make sure that developers correctly specify deletion behavior in all the data they store? Well, we built a framework called DELF. Incidentally, DELF is short for Deletion Framework because naming is hard. So DELF builds on a declarative API. And what this means is, instead of directly writing to a data store, developers give a static specification of the data they want to store and how it relates to other data types. And that specification describes how the data should be deleted. We, in DELF, then validate those specifications, both statically and dynamically. And then we actually execute the deletions in centralized, procedurally generated code. And moreover, the deletions that we generate automatically support restoration for a limited time period. And so that means we can recover transparently from an incorrect specification. Let me give you an example of one of these specifications. This is in pseudocode for a very simple sort of photo object. It has a name, a storage type, which in this case is tau, Facebook's graph database, an ID, some fields, and some edges. DELF asks developers to add deletion-specific annotations on this DSL when they create a data model. And this means that developers can't create a data model and store data without specifying what should happen when the data gets deleted. And in turn, this means that deletion becomes part of the developer workflow early, before any data is collected. So there's two types of annotation here. Object annotations, the first one, specify when the object should be deleted. And edge annotations, the last three, specify what should happen to related objects upon deletion. So for example, in this specification, when the photo object is deleted, the associated blob, binary large object, in the blob store should also be deleted. And hence the edge from the photo to the blob is marked as deep, which means cascade and delete. There's also an edge from the photo to the user who created that photo. And that edge is marked as shallow, because when you're deleting a photo, you don't want to cascade and delete the creating user. All right, so we have our specification language. How does this help prevent the mistakes we talked about earlier? Well, the first one is omissions. And we discussed this already. DELF statically requires these annotations, which means developers can't accidentally forget to implement deletion. If a developer writes a specification without deletion annotations, they get feedback from the data model type checker. And this feedback helps educate developers about deletion expectations. Another thing we do is perform data type validation. And this detects, for example, a field that at runtime contains a reference to another object. Again, we surface these to developers to ask for deletion annotations. All right, so that was omissions. What about misclassifications? Let's say that a developer designates an edge type as shallow, even though it's supposed to be marked deep. So we have various mitigations here, but let me focus on one, which is the idea of dynamic validation via heuristics. So we introduce several heuristics that can classify an edge type as deep based on data that we collect at runtime. If the heuristics think an edge should be labeled deep, but the actual annotation is shallow, then DELF will flag this to an engineer and alert them of the discrepancy. So compared to the static validation we talked about, dynamic validation generates feedback later, after the data have been collected. But the advantage is there has better detection capabilities, because we can find edges that are marked incorrectly, even though they aren't statically incorrect. Nothing is statically wrong with the specification, but at runtime, we can heuristically predict that an edge should be deep instead of shallow. As before, when there's a discrepancy, developers get notified by DELF to correct the annotations or mark this as a false positive for the heuristic. What about the other way around? Developers may also designate to delete data that should be retained. So in the paper, we actually show in a case study that this sort of mistake can be twice as common as the ones leading to retaining data that should be deleted. Again, we have both static and dynamic validation techniques, including heuristics. But in addition, in DELF, we keep these restoration logs, which for a short period of time can be used to undo any deletion. And this is our main protection against data loss. It allows developers to quickly recover recently deleted data with very minimal effort. And then finally, and just briefly, developers may also fail to execute the specification they provided. And the general theme here is that because deletion is not a one-and-done process, DELF will actually execute the entire deletion specification on behalf of the developer. So at the start, an incoming request comes to a DELF API to delete a top-level object. DELF will immediately hide that object, and it will use read time checks on child objects to hide them as well. Over a period of time, DELF will then asynchronously traverse the graph and issue point deletes. While it issues these, it will record the deleted data in restoration logs in case it was an erroneous deletion. And we'll continue this traversal until all the necessary deletions occur. Any errors are retried. If they're non-transient errors, we surface them to engineers to fix. So, I told you about how DELF should prevent deletion errors, but does it work? And we go into much more detail about this in the paper, but in summary, the answer is yes. So DELF is deployed in production, and it's powering deletions across diverse Facebook products. While we were deploying it, we fixed missing specifications for thousands of edges. The static validation corrects developers nearly 2/3 of the time, helping to educate them about deletion expectations, but also preventing incorrect or missing annotations from being committed. Dynamic validation heuristics discover most annotations independently, and the restoration logs simplified user data recovery in nearly all the data loss incidents we looked at. So that's pretty much everything I had. Thank you very much for watching this talk. Please feel free to fire any questions to me at any point via email, or if you're attending this presentation at the scheduled broadcast time, you can use the magic USENIX tools to ask questions to us over chat. And with that, thank you very much.